Hey everyone, this is Daniel for Rock the JVM, and you are watching part 2 of the introduction to Kotlin Coroutines. This will follow the previous video that we ran on Kotlin Coroutines, and in this video we're going to talk about cooperative scheduling, cancellation, and the Kotlin Coroutine context. Now, as before, the objective of this video is to introduce you to Kotlin Coroutines, to how they work, and so on and so forth. So the assumptions are that you know some basic Kotlin, the essentials of the language, and you have some solid computer science fundamentals, especially threading, because Kotlin coroutines are a nicer abstraction over JVM or operating system threads. Now, as always, with Rock the JVM videos, I recommend that you write code with me to get the best out of this video. And whenever you need to refresh your memory about the concepts, just refer back to this video or the previous one, or the extensive written form at the blog with the link in the description. Now, without further ado, I'm going to get back to my development environment, and I'm going to continue where we left off in the previous video. Now, in the first part, we discussed what a coroutine is, which essentially is a lightweight thread. So a thread is a heavy-handed data structure managed by the JVM and the operating system, and running parallel and concurrent applications on operating system threads is pretty difficult because scheduling threads is expensive and so on and so forth. And coroutines are easier to schedule, manage, kill, suspend, start, and so on and so forth. So we prefer this coroutine abstraction to operating system threads. And we discussed how we can start coroutines. We discussed suspend functions, delay functions, and yielding points, which is also the subject of this video. How you can start coroutines inside coroutine scopes, which are essentially a standalone environment for coroutines, which will block until all coroutines finish within that scope. We talked about some coroutine builders, for example, the launch directive and the async directive. We also talked about parent and child coroutines and a bunch of properties in that scope. Now, in this video, we're going to discuss two different aspects of coroutines. One is cooperative scheduling. Now, in regular threading, that is on operating system threads or JVM threads, the scheduling model for threads is called preemptive, in the sense that the operating system will decide when a thread has finished execution, and it will simply stop that thread, save its context, get another thread to run on the CPU, and then when it's done, it will then resume the previous thread, resuming its continuation or its context with a stack and so on and so forth. Now, this preemptive scheduling is very expensive, which is why in coroutines land we have the cooperative scheduling, in which coroutines yield manually. That is, the coroutines will yield control over the thread that they're running on at a yielding point, which is usually a suspend function. Let me give an example. Let me define a little routine. So I'm going to define a suspend function. I'm going to call this working hard. Now, this working hard coroutine will have a simple logger. So I'm going to say logger info. I'm going to say working. And I'm going to run a CPU intensive computation, which of course, for this example, I'm going to simply have a while true, and I'm going to do some hard code here. So I'm going to keep running some code, and in this case, I'm not doing anything inside this while true. And then I'm going to say delay for 100 milliseconds, and then I'm going to say logger info. I'm going to say work done. At the same time, I'm going to also run a suspend function called, let's say, take a break. So take a break. And again, I'm going to have a logger info, and I'm going to say taking a break. I'm going to wait for a second. So I'm going to say delay for 1,000. So 1,000 milliseconds. And again, another logger info, let's say break done, so that I'm done taking a break. All right. Now, I'm going to run two of these coroutines on a coroutine scope with a single thread that both of these coroutines will have to manage. So they will, in theory, have to cooperate. So I'm going to give an example of what happens if you don't have a yielding point, which is here in while true, and what happens when the cooperative scheduling does not yield inside a coroutine that is supposed to give space for another. So I'm going to have a suspend fun. I'm going to call this work hard routine. And I'm going to have a val, I'm going to call this dispatcher, and this dispatcher will be essentially a thread pool on top of which these coroutines will run. And this dispatcher has the type coroutine dispatcher. And the coroutine dispatcher is the Kotlin native thread pool for coroutines. And I'm going to use dispatchers.default, and I'm going to modify that. I'm going to say limited parallelism with 1. So I'm going to force one thread for both of these coroutines. So I'm going to launch both in a coroutine scope. So I'm going to say coroutine scope, and I'm going to say launch on the dispatcher. And on this dispatcher, I'm going to say working hard. And I'm also going to launch another coroutine. So launch on the same dispatcher. I'm going to say take a break. Now in main, I'm going to call this work hard routine. So work hard routine. And we would expect, if we had 2 threads at least, so if we had 2 threads, each coroutine would take 1 thread and they would do their own job. And this working hard, of course, would never finish because we have an endless while true. But this take a break will also run at the same time. So with limited parallelism 2, let's give this example first, we would see both coroutines running at the same time. Let's see. So I'm going to compile and run. My compiler is cold. All right, so we have taking a break, working, breaking, done. Now, this working thing is still doing the while true. So as you can notice, the application never finishes. So I'm going to have to stop it myself. But if I force this limited parallelism to 1 instead of 2, then that means that whatever coroutine ends up starting first, which is the working hard, will end up taking this sole thread and it will never yield. Therefore, this taking a break coroutine will never get a chance to execute. Let's run this. So notice that we have working now, and the take a break coroutine never has the chance to run because this working hard never yields inside this while true. So in order to manually yield, we need to add a suspension point. And the suspension point is usually a suspend function such as delay. But since we never get here because of this while true, then we never get the chance to yield, therefore never giving a chance for take a break to also run at the same time. Now let's insert a delay inside this while true, for instance. So I'm going to copy this working hard, and I'm going to call this working nicely. And inside this while true, I'm going to give a delay. So I'm going to say delay with 100 milliseconds. So give a chance for the dispatcher to run another coroutine. Okay, so at this point, instead of this working nicely, I'm going to create another suspend fun. I'm going to copy most of this stuff, and I'm going to call this work nicely routine. And instead of working hard, I'm going to say working nicely. And in main, I'm going to call this one instead. So in the work nicely routine, we'll now see that both coroutines will have the chance to execute on this single thread that we have at our disposal. So let me run the application again, and we will see both coroutines going at the same time. So we have working, taking a break, and break done, of course. Now, the working coroutine is still running, which is why the application never finishes, which is a bit of a cheating because we are taking a break while working. It's like taking your laptop while sitting on the toilet or something. But whatever, everyone with their own routines, I guess. So even though we have a single thread, both coroutines can run at the same time because we're yielding in between them with a suspend function such as delay. Now, we have a compiler warning here because this declaration needs an opt-in to the experimental coroutines API, so I'm going to add this annotation if you want the compiler to play nice with you. Okay, now speaking of dispatchers, they are essentially the thread pools on top of which coroutines can run, and there are at least 3 different kinds of dispatchers that you can use. I'm going to define them as plain vals, although we're not going to schedule any coroutines on top of them. I'm going to have a simple dispatcher. So simple dispatcher, this is dispatchers.default. This is for normal code. So normal code means that the coroutines are either short or contain yielding points, such as delay functions or other suspend functions. So short code or yielding coroutines. This is the kind of dispatcher that you should normally use in your code. This is why it's called dispatcher.default. And of course, dispatchers will also have some modifiers, for example, limited parallelism and so on and so forth. We also have a dispatcher specifically aimed at blocking code. So I'm going to say blocking dispatcher as dispatchers.io. This is for IO bound code, and this is for blocking code. And examples of that include database connections or long-running computations. This is what you should use for long-running coroutines that you know are not going to yield. So you will need to have your own dispatcher.io for blocking code and dispatchers.default for any sort of normal code. So for example, if you're running a web service and the web service also interacts with the database, you should use dispatchers.default to run your normal business logic, which I assume will not take that much time, and use dispatchers.io to schedule the insertion to a database or the reading from a database and so on and so forth for these long-running computations to speed up the user experience. Okay. You can also build your own dispatcher, like custom dispatcher. And this custom dispatcher can be built on top of an execution context. So you can do executors from javautil.new fixed thread pool, and Java folks are building executors very easily here. And the Kotlin library will have an extension method on top of the executors as coroutine dispatcher, which is simply just wrap this executor service into a coroutine dispatcher that the Kotlin runtime can understand. So this is very easy to build on top of your own thread pool. So you can define your own fixed thread pool or work stealing thread pool or whatever. All right, so you can define your own logic there. So this is with cooperative scheduling and dispatchers. The next thing that I want to talk about is cancellation. So you can cancel a coroutine while it's running. Now, there are some properties and some gotchas with that. So let me define some example. I'm going to have a suspend function. I'm going to say that while I'm working, I forgot the birthday of my friend, and therefore I need to stop working, go to the mall, buy my friend a present, and then maybe resume my work. So I'm going to say, let's say, forgetting friend birthday routine. And I'm going to start a coroutine scope, and I'm going to have a launch for working nicely. So I'm going to say launch for working nicely. So working nicely. And I'm also going to launch. And let's say that after a certain while, maybe if I'm being notified and my notification will be very rudimentary, I'm going to simply call a delay function for 2 seconds. And after 2 seconds, I remember I have a birthday today. And then I need to cancel my working nicely routine. And therefore, this thing needs to be associated to a val. I'm going to call this working job. So a coroutine can have a handle in the form of a job, and this job can have methods, and this job can be, for example, canceled in this case. So I'm going to say working job.cancel, and then I'm going to say working job.join. I'm going to explain how cancellation and join works, and I'm going to say logger info. I say I forgot my friend's birthday buying a present. Okay, so this coroutine scope will launch 2 coroutines. This is pretty easy. Now, when you call cancel on a job, this sends a signal to the coroutine to cancel. Now, this doesn't interrupt the coroutine at this point, but it rather will cancel or stop the coroutine when it has a yielding point. So cancellation happens at first yielding point. And then you can optionally join the coroutine to wait for it to cancel. So at this point, you are sure that the coroutine has been canceled, or stopped for that matter. So either finished or canceled. And only then can you go actually buy your friend a birthday present. Okay, so this has its first gotcha because the signal will be handled at first yielding point, which means that if your coroutine doesn't have a yielding point, it cannot be canceled. Let's run this example first. So I'm going to have forget friend birthday routine. So I'm going to say forgetting friend birthday routine, and I'm going to run this application exactly as it is. So we're going to see working here. And after 2 seconds, we say, I forgot my friend's birthday, buying a present now. And notice that the application is now finished because the first coroutine has been canceled. So cancellation works. So you can cancel a coroutine by calling cancel on the handle of that coroutine. But let's test the gotcha as well. So I'm going to copy most of this stuff. And I'm going to have a comment here. So if a coroutine doesn't yield, it can't be canceled. So I'm going to say forgetting friend birthday routine uncancelable. Cancelable. And I'm going to say, instead of working nicely, I'm going to say working hard. So working hard with that while true without the yielding point. And this has the same logic, right? So we have sending a signal, but it will never be handled. So this will send a signal to the coroutine to cancel. Cancellation happens at first yielding point, which is never. And because you're calling join, this will essentially semantically block this coroutine because the working job will never be canceled. So this line will never be printed. So let's call this in main and let's see what happens. All right, so we have working, and notice that the application is still running because the working job never yields, and my laptop is probably going to take off because the while true doesn't have anything inside. So notice that the forgot my friend's birthday is never being printed. I think I killed this application too early because I waited for 2 seconds. I'm also going to say logger info. I'm going to say trying to stop working, just to see that the buying a present now, me leaving the building is not going to happen. So trying to stop working, and this logger info never gets the chance to run because the cancellation never happens. All right, so I think I proved my point. Now, cancellation has its own set of properties and gotchas with respect to resources, because a coroutine might be delegated to do something with a resource, such as a database and so on and so forth. So if you want to cancel that, you need to make sure that you want to close resources. So I'm going to define a class, I'm going to say called desk, because I'm using the desk as a resource to do my work. And I'm going to implement the interface auto-closable from JavaLang. And I'm going to say auto-closable, and I'm going to have my constructor. I'm going to say logger info. I'm going to say starting to work on this desk. And then I'm going to implement the close method. So I'm going to say override close. And I'm going to have a logger info. I'm going to say cleaning up the desk, because if I'm leaving for the mall to buy my friend a birthday present, I don't want my desk to be cluttered and disorganized. All right, so I'm going to have a suspend fun. I'm going to have, I'm actually going to copy most of this stuff. So I'm going to start from the working nicely one. So I'm going to say forgetting friend birthday routine with resource. All right, so I'm going to have my coroutine scope. But I'm going to instantiate my little desk. So I'm going to say val desk equals desk. All right. Now, this desk will be used as a resource for me. So inside the coroutine job, I'm going to say working job launch working nicely. So instead of just doing working nicely, I'm going to use the resource here. So use the resource here. So I'm going to say desk.use. And desk.use will have my parameter here. I'm going to use that as an underscore because I don't really care about the desk itself. I do have an instance here, so I could use it inside the code, but I don't have anything to do with it in particular. Now, this resource will be closed upon completion of the coroutine. So when the coroutine finishes or is canceled, this desk will be automatically closed, which is a big deal because with resources, you don't really want to handle the closure of this resource when the coroutine finishes inside this code, because otherwise the code will be very hard to read and understand and so on and so forth. And this is also a mental burden for us programmers. So rather, you would build this resource as an auto-closable, and the resource will take care to close on its own once you implement the close method, therefore freeing up mental space for you to just focus on your business logic. So let's prove this. I'm going to run this in main so that we can see what's happening here. So I'm going to say with resource, and we're going to instantiate the desk. We're going to see some log lines there. So starting to work on the desk, working, and then I'm going to say cleaning up the desk first. So notice that upon cancellation, the desk needs to be cleaned, and then I'm going to say running to the mall to buy my friend a birthday present. This is very, very, very important. So resources are a big deal, and you should use these resources inside coroutines. Now, you can also define your own cleanup code in case of completion. So you can close your resources manually if you want. You don't necessarily have to use auto-closable, and you can run arbitrary code inside these sections that I'm going to show you. So given the handle of the coroutine, you can say working job dot invoke on completion. So this is essentially a callback, and the callback takes a throwable which can be null. So I'm going to say exception, which is a throwable with a question mark. That is because upon cancellation, you will make the coroutine throw a cancellation exception, I think it's called. So you can handle cancellation here, can handle completion and cancellation differently depending on the exception. All right. And then you can say, for example, desk.close. Or you can use a logger info, let's say, make sure I talk to my colleagues that I'll be out for 30 minutes, for example. And in this case, I'm going to run my application as well. And we're going to see this log line being printed as well besides desk close. So after 2 seconds, notice that we have cleaning up the desk. So the resource gets cleaned up first, and then make sure I talk to my colleagues that I'll be out for 30 minutes. All the resources that you use with desk.use and other resources.used will essentially be queued inside the coroutine when they are to be released in case the coroutine is finished or canceled. All right. So you can also define your own cleanup code. Now, speaking of cancellation, cancellation will also propagate to child coroutines. So I'm going to say cancellation propagates to child coroutines. Now, in the previous video, we defined child coroutines, so you can check that out first. I'm going to give an example with a suspend function. I'm going to say drink water because I want to drink water. I want to stay hydrated while I'm working. I'm going to say while true. So while true, I'm going to have, let's say, logger info. I'm going to say drinking water, and then I'm going to have a delay for 1 second. So let's say I want to drink water every half an hour, and I'm going to say water drunk or something like that. Actually, I'm going to keep this just to one line. Okay. Good. Let me run my suspend function. So I'm going to start with the forgetting friend birthday routine, the basic one. And I'm also going to launch my drinking water inside this working nicely thing. So I'm going to say forgetting birthday routine and stay hydrated or something. Stay hydrated. Okay. So this working job is going to be a launch. Now, inside this coroutine, I'm going to launch to child coroutines. So I'm going to say launch working nicely. All right. And I'm also going to launch drink water. So I'm going to say drink water. So I want to work nicely while drinking water. And of course, I want to stop them both and forget my friend's birthday and rush to the mall and buy this friend a birthday present. Now, when I have this handle, which essentially is a parent coroutine over these two child coroutines, if I cancel this one, I'm going to cancel both working nicely and drinking water, of course. So needless to say, I'm going to run this in main, and we're going to see both being canceled. So drinking water, and after 2 seconds, I forgot my friend's birthday, and the application is fully stopped. All right. So this makes perfect sense. If you want to cancel a parent coroutine, it will naturally cancel all the child coroutines as well if you nest your coroutines. Now, one last bit that I want to talk about is coroutine's context. The coroutine's context is essentially a data structure that the coroutine can use to get started with. For example, the dispatcher and the coroutine name if you want to track those in the logs. So I'm going to give an example. I'm going to say suspend fun. I'm going to call this asynchronous greeting. Let's say I want to say hello to everyone, and I'm going to have a coroutine scope, and I'm going to launch a coroutine, and I'm going to say logger info. I'm going to say hello everyone. Okay, now with this launch directive, I'm also going to pass some arguments here. So I'm going to say coroutine name. I'm going to say greeting coroutine. So notice that you can give this coroutine a name with this coroutine name parameter. This is a plain data structure. And this also has some nice methods, for example, plus that will allow you to combine two coroutine properties. So one is coroutine name, another property. Another property is the dispatcher. So I'm going to say dispatchers.default. So you can launch a coroutine on a particular dispatcher by passing this one as a parameter. And these two can be combined to form a coroutine context. So these two combine a coroutine context. And the coroutine context is a bigger data structure than just these two. I just gave an example combining two separate properties. And if I call asynchronous greeting in main, we're going to see in the logs that the coroutine name is called greeting coroutine. All right, so notice that the default dispatcher worker 1 at greeting coroutine so that you can track the coroutine more easily. Now, the coroutine context, which is, for example, the name, the dispatcher, and so on, they can be inherited in child coroutines. So I'm going to say suspend fun. I'm going to say in context inheritance, or I'm going to say demo context inheritance, and I'm going to have a coroutine scope. Inside, I'm going to launch with these properties. So I'm going to have coroutine name greeting coroutine. Actually, the dispatcher default is being supplied by default. So I'm going to say coroutine name with greeting coroutine. And I'm going to have a logger info. I'm going to tag this with parent coroutine. I'm going to say hello. And inside, I'm going to launch another one. So I'm going to say launch logger info. I'm going to say child coroutine. I'm going to say hi there. And I'm going to delay for, let's say, 200 milliseconds and another logger info. I'm going to have hi again from parent, and I'm going to also tag it with parent here. So parent coroutine, and just that we can track these log lines to belong to their respective coroutines. Now, this context inheritance means that the coroutine name called greeting coroutine will be inherited to all child coroutines. So here, the relevant bit is the coroutine context will be inherited here, which means that this child coroutine will also be called greeting coroutine as its parent. So if I run this application, we're going to see greeting coroutine for both. All right, so we have greeting coroutine #1. This is coroutine 1. Greeting coroutine #2. This is the child one, which also has the appropriate tag in the log. All right, so this is the essential gist, that the coroutine context will be inherited. However, you can also choose to override some properties. For example, if you want to pass another coroutine name than the parent, you can say coroutine name, and you can say child greeting coroutine. And this means that this coroutine will obviously have another name that you can track in the logs. So we have greeting coroutine #1, child greeting coroutine #2. So there is some essential inheritance for the coroutine context between parent coroutines and child coroutines if you want to pass these properties in your nested coroutines. All right, folks, so this was a comprehensive introduction to Kotlin Coroutines Part 2. I hope you liked this video and found it valuable. If you did, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this. And check out my website and my blog at rockthejvm.com. I have literally hundreds of hours of free videos on Scala, Java, Kotlin, and everything in between. I'm Daniel, and I'll see you soon.